little bit of history. And a view of the more fancy techniques that are now available, some of which we can practice actually, if not later this afternoon, definitely on Wednesday. So visualization in general is not something new. Of course, in the very old days, and we know these famous drawings on the walls of grottos were made many years ago, and of course these are visualizations of animals or people. We visualize, of course, the universe, but visualization in general is basically trying to sort of have an idea that you have into a picture or a graph so that you can remember it better, or to show other people what the essence is of what you want to bring across. And if you look for some basic definitions of visualization, you find many, and I picked three to form a picture of someone or something in your mind so you can remember the person or that instance better, or making a presentation of numerical data like graphs, which we are all very much used to and we do all the time, or representing, and that is something we don't do, but it's also visualization, abstract business of scientific data as images that help understanding what it is. And of course, people make a lot of use of visualization. I mean, the signs in an airport that tell you where to go often have little pictures to help you go. It's not universal, because different airports have different pictures, but they help you find your way around. But let's now sort of concentrate more on the astronomy part. So 1D, 2D, and 3D data, and especially multiple dimensions. How do you visualize that in such a way that you can actually better understand what your data tells you, and in a way that you can interact with the data, because it's all about research and going through your data and finding things, but also being able to mark things if you think they are exceptional or strange. And so the visualization has to be interactive, also to make it useful for scientific research. And that's different from making nice pictures that you show people. Of course, with all the things happening in astronomy all the time, we see pictures in the newspapers. Awesome pictures, and people are always asking me, what does it mean? And it brings you attention. But the pictures are never meant to basically do scientific research. You need a different kind of picture, and you need to be able to interact with that. So I think that is what visualization, the type I will be talking about, is more about. But this is old school. This is not really as old school as, for example, my thesis. But in the old publications of neutral hydrogen, people published their individual channel maps. As not as pictures, but as contour diagrams. And so you see here, this is NGC 3198. It will come back later in some of the graphs that I showed. And I picked it on purpose because this is the galaxy that got a publication where the rotation curve of the galaxy measured from the neutral hydrogen goes way out, far beyond the optical disk, and stays flat. And that is sort of the first clear. Not the first example, but a very clear and worked out example for the presence of dark matter galaxies. And what you see here is different velocities, starting at low velocities here, increasing to higher velocities to the bottom. This is the continuum that has been subtracted from all these other data sets. And you see the H1 changes its shape depending on where you are in the galaxy. One part is approaching, the other part is receding, and the central part, we see this sort of simple structure. And for a rotating disk, this is what you expect to see. You can fit it, of course, as a rotating disk as well. So that is now old school. People don't publish their channel maps anymore, but now, of course, they often publish the data, so you can grab the data and actually view it with your own viewer. But then it's important to have the right viewer. So that's what we will be talking about. This is a bit more modern. So it's a composite. It's still a visualization in the old school type of way. with contours, a loose hydrogen distribution, and a fat contour marking the level of 1 solar mass per square parsec in surface density. The velocity field, so this is the different galaxy, by the way, the receding and the approaching part. It shows a cut where one axis is along the minor axis, or no, along the major axis, and this is velocity. So you here see the approach, the receding part. So this is a cut through the data along the main axis of the galaxy. Let me just push this away. The distribution of H1 radially average, so you see how the density is flat in the center and then drops out and has its phase sort of extended image in the outer parts. And this is what you would observe if you had a big telescope with a large field of view with a single pixel, like a large, say, 100, 200 meter telescope. You point at this galaxy, it's not resolved, but you measure all the H1 at once and you get a global profile, which you also can construct if you have more detailed data from the data itself. So this is sort of the old school visualization. And a more modern version of that is something that comes out of what is called the Sophia imaging pipeline. This is a set of Python scripts, which, and I'll come back to Sophia. Sophia is a source finding software which we will be talking about later this week, and also try to give you some demonstrations. That finds actually sources in H1 data cubes. If it's a single galaxy, it will find a single source, but if it's multiple galaxies, then the modern surveys will have large fields of views with lots of galaxies in a single field of view, and I'll show you an example later. Then for each galaxy, the Sophia finds where it is, and it masks that region, and within that mask and within the area that contains all the emission from the galaxy, this pipeline basically does the further analysis. So it produces color density maps, velocity fields, signal to noise maps. Oh, this is the signal to noise map. This is a dispersion map. So that is basically the width of the profile. Integrated profiles, and also velocity cuts along the major axis and the minor axis. So all that data is then displayed in one graph, and in one glance you can see that compared to not so deep optical data, how extended the galaxy is. You can see that the rotation, which is also visible if you plot distance along the major axis versus the velocity. So basically a slice in that direction, and a slice perpendicular, you see basically that it's all at the same velocity. If there were outflows, you would see those there, and this will become extended well, you would see things here and here which are not visible now. And the red contour is basically where the Sophia mask that was used to isolate the signal was determined. So it gives you an overview of everything you have in your source. Data, of course, is 3D because you have various frequencies, which translates into velocities of your data. And since it's a spectral line, depending on what the rotation is of the particular part of the galaxy or object that you observe, it will appear in different channels. But basically, that translates into a three-dimensional structure in your data, where one axis is frequency or velocity, and the other two axes are a deck on the sky. And you can also visualize the volume in your data cube, because the galaxy itself is a volume, and that's what's happening here. This is with a piece of software called Slicer ASPO. It's no longer maintained, but it still has versions that work both under Linux and on Macs that are downloadable. And this is the site where you need to go. This is the first view of M101. So this is the M101 galaxy. The center is here. It's a bit lopsided, so there's extended low-level H1 one part. This is the companion galaxy, CC 5474, if I recall correctly. And that's the front view, but if you rotate this, which has happened here, then basically now velocity is sort of along this axis. RE and Ek are here. This is declination. This is our ascension. You can see these structures, which well, let's first go back. What do you expect for a rotating disk? We saw the channel maps. It's sort of like a pancake, but it will not be flat because it's rotating. It will be curved toward lower velocities on one side and higher velocities on the other side. So in 3D, it will look like a warped pancake. And that's the normal rotation. And that's sort of what you see here. That's sort of the warped pancake that you see here. That it's hollow here because that is the rotating part. And it bumps up here, so that's the receding part. So there's a bit of a curved shape. That's general rotation in the disk. But everything which is not rotating in the same fashion will basically stick out in the velocity direction. And that's what you see here. Is this enormous bow of gas, pieces here, and there are pieces there as well. It's different places. But this gas that is at a different velocity, and this is considered to be well, it's difficult to determine exactly, but it's not co-rotating with the gas in the disk, so it may be an outflow or an inflow. And in 3D, you see it immediately. When we discovered this was a long time ago. Renzo Cici and I were looking at basically channel maps, and we fled through the channel maps on a display which is like this. So you then see the different pieces, and then very faint. Actually, this here is that high velocity gas that you see here. This showed up at channels where we didn't expect any H1 anymore, but it was very faint. This data has much better quality than the data we had at the time. And so that caught our eye, and we focused on that, and that led to the discovery of this high velocity gas in M101. But if we had had this 3D display, you would have seen it right away. You just rotate around the galaxy, and you see everything that is not in the pancake, in the warped pancake, the rotating disk. So that is very powerful to also be able to do a volume rendered realization of your data. Now let's go back to some of the basics. How do people get the data? And most people probably get their data in a FIS file. Who doesn't get his data in a FIS file? There is, of course, HDF5, which is a more modern format, which eventually will, for various reasons, be more popular in the future. But right now, most of the data, at least in the radio that we get, is FIS. Which is not a kind of data to easily work with, but once you load it into a software system, then it's all there in the native format, and you can work with it. And there are lots and lots of pieces of software to look at FIS data. I will not go through the details of those. I only want to point out that there are many possibilities if you want to look at the contents of the FIS file. If it's a single image, then lots of them will be fine. If it's a three-dimensional or more-dimensional image, then only a few are really useful, and those we will be focusing on this week. And some of those you probably are already very familiar with. I mean, Tom and I this morning looked at some pictures, and the person showing us the pictures was using DS9. So he is already very familiar with showing various types of data using DS9, which I will not discuss in detail, actually, as a FIS viewer. So the ones I will talk about actually are Karman, and that's a set of routines, and the ones that I use a lot are KVIS and KPV slice. So you basically software, you type in the command line, and it spawns a window where you can view your data. Karta, which I think is sort of by now a system many more people are using because it is becoming more and more versatile. It's also becoming harder and harder to learn how to handle it. I'm not very good at using Karta, but it has many different possibilities for looking at images and also data cubes. Slice also, I showed you the picture, and I could give a demo of that, and I'll have some pictures of galaxies that were made in Slice ASTRO, like the ones of M1 that I showed. And what I think is really, for many reasons, very helpful for looking at spectral line data. And that could be H1, but it could also be molecular lines. It could be optical IFU data, although there, since you have many lines, things become more and more complex. The way what you see in 3D is to go into virtual reality and basically be inside your data cube. And I'll show you why that for complex systems it gives you a better view of the complexity of your data. So those I will touch upon a little more. But these others, like DS9, the software system for spectral line analysis, Gypsy. There is a slice view and visions, and I'll show you a picture of those. But we will not use that this week because you have to install Gypsy and all kinds of complicated things, and it makes it harder to get access to it. Whereas installing Carta is fairly straightforward and has many of the features, not all, but many of the features that you would like to use. So here is a channel map of NGC 5907. This is an edge-on galaxy, and it shows the inner part of the galaxy, and this is the warp. And actually, it's not a simple warp because there is also low-level extended gas, which all of a sudden in the outer parts goes into the other direction. And if you look at the other part of the galaxy at other velocities, which is down here but not shown, you see the other side of the warp which bends in the other direction. So it's really like you used to see. The warps are two-sided and antisymmetric. This is the same channel in various display packages. There is DS9, Carta, KVIS, which I mentioned, and this is a panel that goes from KVIS where you basically have your data that you can all set all kinds of things like you can display contours, you can change the grayscale, and so on and so forth. QFIT's view, and so those are a few, but I will concentrate on Carta and KVIS, and also this week I think we will be showing those, but not the others. And in Carta, for example, you can already see it here, but I'll have another display. There's other features of the data that are displayed in the same window. So here is one special thing that DS9, for example, I don't think has, and if I'm wrong about that, please correct me, and that is to be able to display simultaneously, say, either a channel map or the integrated H1 map of a galaxy, and then draw with the cursor a line, and then display in another panel the emission along that line, but now as position along the line versus velocity. And since this is the major axis, we miss the warp in this case, but the main disk is followed. You basically see the rotation curve, the projected rotation curve, not the intrinsic rotation curve. Then you have to make a correction for sin I, but this is a natural galaxy, so sin I as well. So you see the rotation curve. And you can see here it's still a bit of faint stuff. You pick up a little bit of the warp in that direction. This is the viewer in Gypsy Visions. That has another feature which is not like this, but here you can display at the same time a channel map. And with the cursor you can move through the various channel maps. And on the sides you get this, basically literally the side view of your cube. So this is RA. This is depth. This is also array for the lower panel, but then this is velocity. So basically, it's like putting the cube on the side and looking through it from the side. And the same here, but then, of course, in declination versus velocity. And you can move the cursor in any of these panels and move back and forth, and then the other panels will follow the cursor. So you can explore your data that way. But it's still not the same as looking at the entire volume, where you see much better coherence in phase structures. But this is already for spectral line data. I think I use this a lot. And then you actually go with the cursor in this, rotate the slice direction. This will basically follow right away. So you can actually explore your data cube by moving around with the line along which you play. the data, the emission each one. Carta can do this now as well. And I didn't know that, but Tom told me yesterday that if you do the preview of your slice, which you can do, and it's the same as the final view, and then you then move your selection, then the preview changes with the selection. A bit slower than KVIS because that has to do with what's under the hood and how it calculates it, but it has that capability as well. So that is already quite powerful. That's the three-dimensional data. This is the same in KVIS now. This is NGC 3198. And just to give you a better view, and you see indeed that rotation curve peaks and then stays flat all the way out to the edge of the disk. This is data that I took from the Halogas survey, which is now public, and you can basically get the data cubes of all the galaxies that they observed quite deep and explore and use it freely. So now Carta, the advantage of Carta is that in addition to the view on the data, you can display other things. And these are say standard widgets that are here, but you can remove these and put other in place. So you can basically tailor it to the type of analysis you want to do with the data. What is displayed here is basically the statistics of the pixels in the entire data cube. And with these, you can set this as a standard way of setting the various display transform functions. But you can also basically move this with the cursor to lower and higher values, and also the minimum cutoff. And here you can choose whether this is logarithmic, whether it is linear, logarithmic, square root, and there are another couple of options. So you can basically tailor the way you translate intensity of the data into color yourself, and suit it to what you want to see, and then explore the data. And these are it's at the fixed position. The cursor is not shown here, but if you move the mouse around, the cursor moves around, and these graphs move with the cursor, and they are basically all the pixels in this is X, all the pixels in Y. You can also replace this by all the pixels in velocity, and then of course you have a spectrum. So you can tailor that to what you like. And this is basically a panel where you can either start a movie by hitting play, or move this slide bar to move back and forth through the data cube, and this will change right away. Another option, and that goes back to sort of the channel maps I showed in the beginning, and I think it's this icon here. If you press that, you get channel maps, and you can choose how many you want to have. And this is an example. These are the channel maps of this Halogas data of NGC 3198. And you can choose the number of panels in X and in Y that you want to display. So it could be 4, 8, 9, whatever. I chose it such that indeed you go from hardly any signal to hardly any signal at the low velocity end. You can also superpose contours on this if you want to. So it has lots and lots of features. But as I said, it's hidden behind all these various buttons, which bring you into the various pieces of functionality. But there is a lot there, so it's hard to learn exactly. If you want to do a couple of simple things, at first it's hard to learn how to do it. I'm not very experienced with Carta, but in the last couple of weeks I tried things a little bit, and so if necessary, I think I can give you some help. And maybe during this week we'll discover more about its features, but it's still fully being developed. And one thing about Carta, which is, I think, for big data in the future, an important thing, that you will be able to access data which is somewhere else. But Carta runs then also somewhere else, but you get all the information through a fast web link. And that for many big data survey type of data sets, that is going to be the future. You're not going to pull all that data over and do it locally, but you want all the tools at another place where there is enough computing power to do it smoothly, and then only get the pictures sent across the web so that you can interact with the data that way. And this is an example of this view. This now shows a single channel of NGC 3198. And this is the region, they call it the region, but it's basically a line through the data cube. And this is the position velocity diagram produced by Carta. And if you do it as a preview, not generated, but do it as a preview and leave the preview up, and you change this, this will change it as well. So that is a good way to explore what's in your data. And for example, you can easily suppose this is an edge of galaxy. You want to see what the rotation is doing above the disk. You only have to move this up with the cursor, and this will show you right away what the rotation above the disk is doing. Yes.
Sorry, can I? Have you? So you said this Carta thing like connecting to the remote server. Is that already implemented or it's not? Is it?
I think it's already working that way.
Okay, is it like an SSH connection to your remote server and then you can work with that? Do you know? Because I've run into this problem like for ages because like my simulations are very big, so I've had to create like PITS files of like just to decide things that I want to do, but then download it and then work with it in Carta. So I think that's great.
But people working with data from Meerkat, if they don't, often they reduce the data in South Africa on the idea. And the Carta running there and can look at your data locally. And you have the screen and everything, you're in control. But it's the same as if you had it on your own laptop or desktop system. So I think it's already working that way. Now go back to 3D and push the button, then we'll start moving. I think. Yeah. These are galaxies. This is data from Mark van Heijen's thesis, actually. So it's fairly old data, but visualized with slides of ASCO, and then snapshots were made at various orientations of the data cube, and that was basically put into the movie. And you can see, for example, I think this example here shows very clearly that you have sort of this warped pancake, and there's nothing strange here. And the others look like that, although that has some outer stuff in some places. But this is a mess. Look at this, this. Actually, you don't see the galaxy here, but all the gas is in this long filament. And maybe I can try to do that. No. Maybe I can do it here. No. I'll just keep looking at it. You can see that the structure is in some views quite clear, and in other views it's completely spread out. It looks like high noise, but it doesn't look very coherent. And so that's the advantage of being able to look at 3D, and all of a sudden you see very coherent structure. Which, if you look in other ways, if penning through channel maps, you would not have found it as easily as you see it in 3D. So that's an additional advantage that faint structures, because they are coherent still in velocity, show up depending on the orientation you have with respect to your data much more easily if you have a volume rendered or 3D view. And let's make it more complex. This is one of my favorite systems. And that's because I did my thesis on this part of the galaxy, very old data. But the structures that are here, bright, not this, but this structure here, was already visible because that was fairly bright H1. This is M81, NGC 3077 and M82. And because of the interaction, there is all this faint H1 between the galaxies. There's a big starburst here, is the central H alpha from the central outflow. Actually, NGC 3077, it's not here, it's here. So most of this gas is actually at the edge of the galaxy and outside, sitting over here. If I had made a contour plot on this, you would have seen it. And this is basically the front view. Now, if you go and volume render this data, this is data from a mosaic from the VLA, paper by the blog, Fabian, myself, and a few other people. And that's what I visualized here. This is in the slice of ASCO, and it shows the various views that you can put on the screen there. This is a histogram of all the pixels. It looks a bit funny here because you expect a Gaussian distribution, but there are lots of negatives. And that has to do with these two planes that you see here. This is velocity. And so you don't recognize the galaxies, but this broad thing here is M81. Here is M82. This is stuff north of M82, which is flowing out. As you see, 3077 is down here, but you don't see it very well. This is galactic H1. You're looking through the galaxy has H1 as well. So if you are observing at low velocities, you get the galactic H1 in the foreground. And since galactic H1 is very close, it's all over the sky. And so in this data cube, all over the image, you have this very narrow in velocity, but very extended spatially foreground H1. And in the case of M81, you have it at two velocities, minus 56, if I remember correctly, and minus 120. So there are two sheets of local H1 which are in front of the H1 in M81. You can see it here. This is a channel map, and this again is velocity versus I think this is y. So this is declination, and this is velocity versus right ascension. Here you see the rotation of the gas in M81, but then clearly you see these two stripes which are foreground H1, and it's negative here because it's not very well measured by the interferometer. So you get all kinds of artifacts because of that show partly show up as negative structures. Now, what does it look like if you go and immerse yourself in the data? So I made a movie. Now you recognize M81, M82 up here, as you see 3077. But now we start sort of rotating the data. You can see the sheets appearing very clearly. They're not as bright as in the other display, but you can see them here now. And now you see the full rotation of M81. But then the gas between M82, which is here, this is the outflow, but M82 has a broad velocity range in the galaxy itself. The gas between is also coherent. There's regular velocity gradient bridging from one object to the other. The same is true in the bridge to NCC 3077, which is down here. So now you can explore the data. And if you go inside M81, which is difficult to show in a movie, but if you are immersed, you can see it all, you can zoom in and go there. Then there are all kinds of complicated features that you don't see when you move through channel by channel. And also, you don't see very well if you do volume rendering. And the problem is they're hidden. Sometimes there's a structure in front that hides structure which is at another velocity, but along the same line of sight. And the only way to find it is to go through the data and go to that particular place where that anomalous velocity stuff is. And so there's a lot of complex emission in M81 that is hidden if you look at it in the general way people look at the data. And that's the reason I got interested in this VR stuff, because this is the data I first looked at 5-6 years ago in Cape Town. In the very first version of this virtual reality visualization system. So now we're back to the front view, and you see M81 and NCC 3077. And all this galactic stuff is associated. I can go back actually. Associated, you see this stuff here. There's lots of foreground, also cirrus. When IRIS satellite mapped the whole sky, it found a lot of what they then called cirrus, which is basically galactic dust everywhere. And part of the H1 is associated with this faint emission, which is associated with dust in the galaxy. Some of this is, I think that this little bow structure, because there's also H1 there, is associated with you see, and it has the right velocity to be part of the M81 system. And not part of the galaxy. So, yeah. This is another application of the virtual reality viewing. This is a data cube. I think this is the Fornex cluster, but I'm not absolutely certain. Let me start in motion. And you see lots and lots of different galaxies. This is a cluster rich of galaxies, large field of view. I think this is Meerkat data. And you see lots and lots of objects. These objects have all been isolated using the source finder Sophia. And what is shown here now in this visualization is only the galaxies. Now we see everything but the galaxies. And if this is all noise, then you know that the source finding did a good job. If you still see blobs there, this again is all the sources. And what we'll do now is zoom in a smaller section. And by zooming in, the data is so much data is downsampled. You don't see every pixel. But if you zoom in, then and the number of pixels fits with the memory specifications of your system, then you have every pixel in the data is a pixel in viewing, and that's the case here. And then you can start looking in more detail at the Sophia masks. This is a headset that has the various options of doing things, and now you see overlaid the masks that Sophia found within which all the H1 that is found is contained by hand, and I'll show you an example later. You can change the masks as well. If you think, well, this mask should be a bit wider in some place and a bit narrower in another place, then by hand you can take all the various bits and pieces and change it by hand. And here it goes through showing the masks and the objects, and this is without the masks. And probably will go back to the full view. Yeah. And all of a sudden you lose detail because now in order to be able to display the data, it's not fully sampled. And this is one final movie that shows one galaxy only, but it shows how you go about doing editing of the masks. It's called the paint menu. But it's going a bit fast. But now you see the masks here, and there are these things which don't seem very real. So somehow those were picked up by the source finding, but are noise rather than continued associated signal. And you can go in by hand and then remove this. The movie shows how to do this. See, the pixels just disappear, and you see what you're doing. Because there is this transparent grid of the mask superposed on the data. You can also do it the other way around. You can display it in such a way that it shows all the data outside the mask, and if there are little bright pieces there, then you can find those and put them into the mask using this hand painting capability. So that I personally find a very powerful system. And for example, this has been used by Tim Jarrett quite a number of years ago. This was a polar ring galaxy in ASCAP data. You had the central disk, which was rotating just like the pancakes that we saw before. And it has this polar ring, which is in a very different plane. So the rotation characteristics in 3D are also very different. And he isolated the rotating disk by drawing a special mask, and then basically use that mask to subtract the galaxy from the data. And that masking, because it was in 3D, he could do very finely. Sophia cannot do that. It doesn't have the intelligence to separate properly the polar ring structure from the rotating disk structure of the central galaxy. So that's an example where actually doing this by hand is very, very powerful. Now, finally, back to slides for Astro, but in general, what I want to illustrate here is because you can do it in different ways, the power of modeling, but then going back to your data and to be able to show your model and the data at the same time. And if we even go to the point where you use the model to subtract part of your data and see what's left. But before you do that, you don't want to do this blind. You want to look at your data and look at the differences. And this is from the things data, NGC 2403. And I'm jumping ahead, but we'll get back to this later in the week when we talk about modeling galaxies. The disk of NGC 2403 has been modeled with a software called 3D Barometer, which takes the entire cube. Who is familiar with 3D Barometer? You are. So if you and basically fits the rotation of the galaxy to the data in cube. And the model is shown here as the whitish contour, and it's shown as an overlaid surface on the data. And everything which is not fit by the model, which is basically the blue contour in these cuts, is shown because it sticks out of the gray surface which shows the model. And it's shown here as green, and if you turn it around, there's also some stuff at the other side, which now you don't see because the surface that you painted is in the way. And this is anomalous gas on the north west side of NGC 2403, which connects to gas farther out, which is not co-rotating, and it's this gas in this position velocity slides that you see here. Some of it is here, but here it's clear. And this is a rotation curve fit that is used by 3D Barometer. So this combination of modeling and data, but also bringing it together in the same spaces, I think is very powerful. You can do this in a different way. You can run Barometer on the data, and what I've done, I could even show this to you later this week. I've taken the Barometer model and made a mask out of it rather than a surface in a FITS cube, the same size as the data cube. And I put it in VR. And then rather than the Sophia masks, which are from the source finding, it was a model mask. You can play the same trick. You can basically isolate by just telling a software to show everything outside the mask, isolate this feature in 3D and see all the things that are not fit properly by the Barometer model. So there are various ways of doing this. So I'm sort of a bit at the end of the things I wanted to show, but maybe we should have a discussion and sort of try to get a bit, give me a bit of an idea of what we should concentrate on later in the week when we start practicing some of these things. But my summary is that there are many viewers, but only a few of them I think are very useful, and those are the ones I showed. Karma is amazingly old. I think the software was written like 35 years ago, but it's still up to date in terms of what it can do. And a lot of, maybe by now, dinosaurs with lungs like Tom and myself, I thought are using it a lot because it is so versatile and powerful and quick. But Karma is now is having a lot of features that Karma has, and it's easier to install. And of course, for newcomers, is also a requirement. It's not too difficult to install software on your system. Karma can read various formats except HDF5, because when it was designed, HDF5 didn't exist. Slicer Astro is frozen, unfortunately, because the person who developed it went out of astronomy, and it's part of Slicer 3D, which is basically a medical package. But it's written in such a way that all kinds of other people could attach modules to it and use the core software and then import their own analysis tools. And that's how Slicer Astro was built. And now the things we built in the Slicer core system have gone out of tune. It's a very well-known software problem. You have to keep updating your things. Otherwise, if you use other software, you run into problems. But the downloadable binaries still work. And then Ivy is fairly new on the market. The formal first release of Ivy was done about a year ago, and it looks at volumes. The movies are showed. But there are now also is a version, and it's experimental. But I have a binary, and I gave it to Unice that can view the people call it particles. But particles basically is either a simulation or a redshift catalog or any catalog. And basically what it reads is a FIS table. And it displays 3 of the columns. It picks default first 3. So if the first column is a name, then I think it recognizes that it's a name and it cannot display it. So I'll take the second and the third and the fourth column. But you can change that any way you like. So you could, in fact, even look at color diagrams and import a third parameter, maybe color diagrams in 3D, like you do in TopCat, but you can do it in immersed as well. So with that, you can look at for example, simulations. I've used it to look at the solutions of Sophia finding sources on a very big data set. So you have hundreds and hundreds of sources, and I could display in 3D using that software the source parameters. And if you include also the noise, then you can clearly see which part of the space that you choose in 3D. For example, say peak flux versus number of pixels versus the sum of all the pixels within the masks that are being used to find the sources. In that space, noise, and if you include also the sources that were found but later rejected as noise, then you can see the coherence between where the noise is, because you see many things, positive and negative, all bumped together. And then the real sources are in the higher signal to noise areas outside where the noise populates the 3D space. So you can see that right away, also with this. I think that's it. Yeah, this is what I had in mind to sort of bring across, give a bit of a view of what is now possible. And the thing is to go and do it. Find this software and practice a bit and see what is useful for your application. Yes.
Okay, sorry. I think the VR stuff is really cool, and I think like it as in like giving you ideas on how to work with your data and like maybe visualization differently and working with it. It's very helpful, but I have big questions, or like I'm not so sure about like its actual scientific like value, if that makes sense, because. But so the thing is, like, when you do something, right, and you polish it, you want it to be reproducible. And if you're doing it with this VR thing, I think it's very like a personal experience, right? Because like you're basically going through it yourself.
Yeah.
And it's kind of like you see it differently. But then how do you know, or do you, of anyone that has done it, so it's actually reproducible and it's an actual like scientifically proven and like publishable? Or like, do you think it's more like something that you can use for like outreach stuff, or just for yourself to give you ideas, but then you have to work